Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python Part 7. In this lecture, we are going to discuss what might happen if you tried to plug in a neural network into the code we just wrote. I am also going to suggest some exercises for you to try. Because there are so many options, some of this stuff even I haven't had a chance to try myself. But the hope is that because we're such a big class, everyone can try something and we can pool our results together. First, you've already seen that we can plug in TensorFlow or Theano into our Q-Learning script. You also know how to build a neural network in TensorFlow and Theano because we've done this many times in previous deep learning courses. So one interesting thing to try would be to replace our linear model with a nonlinear deep neural network. You might also want to remove the RBF layer, since we expect that a neural network should be able to come up with its own features. One downside to this is the catastrophic forgetting effect. This idea has gotten lots of attention recently because researchers have found ways to successfully implement transfer learning. In other words, they could train an AI in one game and use parts of the neural network to improve training on another game. They then showed that the neural network was still able to play the old game, so the neural network didn't simply just learn the new game and forget the old game. The reason this research is noteworthy is because this is not how neural networks work by default. In a more typical case, we actually expect the neural network to forget how to play the first game. But this forgetting effect doesn't only apply across different tasks. As you've seen, when we do stochastic and batch gradient descent, the cost function can jump around quite a bit. I would say the effect seems to be more pronounced on highly nonlinear regression problems, which is exactly what we're working with now. Ideally, you'd like the data in your cost function to represent the true distribution of the data. When you train on all training data simultaneously, this is actually only an approximation of the true distribution. It's like doing a clinical trial for a drug. You might have a sample from thousands of people, and you hope that they are representative of the population as a whole. So when you use batch or stochastic gradient descent, this approximation becomes even worse. What makes it even worse in this course than a typical stochastic gradient descent is that there is a large bias in the ordering of the training samples. In particular, you're always proceeding from the start state to the end state. There is no randomization, which is recommended if you're doing stochastic or batch gradient descent. So what happens is, you'll train the neural network to do well in a cost that's with respect to the most recent samples, but then you've forgotten about the earlier samples. One thing you might want to try that I haven't tried is dropout. Dropout regularization may be able to help, since it means some of the weights that connect some of the nodes will randomly not be affected during any particular training iteration. You can also try other types of regularization and different architectures as well.